Hello, one and all. Bienvenue à tous. If you're tuning in live, thanks for making the time to join us in your busy day. If you're watching this on YouTube, thanks for stopping by. Whichever way you're joining us, welcome to Post Media's sixth season of Driving into the Future. Today's panel is hydrogen, the missing link, and I'm David Booth, senior writer for Driving.ca. Until now, hydrogen-powered vehicles have been too expensive and not efficient enough to become a significant alternative to EVs. There are also precious few places to fuel them. But what if in one panel we could solve some of these problems? What if we could make our refueling infrastructure cheaper, produce hydrogen so efficiently that a hydrogen fuel cell vehicle would be as energy efficient as a battery-powered car? And what if there was a way to combine the best of both battery and hydrogen technologies in one car so that we could have long range and quick refueling? To enlighten us on these latest breakthroughs, I'm joined today by an august panel of experts. First up is Dr. Robin Hamilton, Chief Technology Officer of Dark Matter Materials. Then we have Pat Donnelly, Business Operation Manager at Verne. Dr. Lorenzo Bartolucci, tenure-track assistant professor at the University of Rome Tor Vergata. And last but not least, Jay Sackett, Chief Engineer of Advanced Mobility, Toyota Motors North America. Welcome to you all, and thank you so much for joining us today. Before we jump in, let me welcome our viewers and let them know we are trying to answer a few of their excellent questions you've submitted. Robin, I'm going to start with you because your company is working on a system that can make pure green hydrogen, the non-emitting kind, using less energy. You call your company Dark Matter Materials. Love the name, by the way. What are the benefits? Does this make fuel cells more efficient? Does it make them greener? Does it make them cheaper? Please.
Well, thank you for having me. First off, I think one of the things we sort of have to talk about are the things that everybody working on green hydrogen have in common. We're trying to lower the carbon footprint. If you look at how hydrogen is produced right now, the carbon footprint is huge. For every kilogram of hydrogen you produce from steam methane reforming, it's about 9 to 12 kilograms of CO2. So that is of paramount importance. So we're trying to lower the carbon footprint. You want to minimize the number of steps. Every time you have a step, you're going to lose efficiencies. We also want to use the least amount of energy possible because not everybody's going to have access to renewables. And electricity, most of the time you're getting it from fossil fuels. So there's a CO2 component to just using electricity. So all of these things have to be minimized. And the way we're doing it is different from electrolysis. It's a thermochemical process. And by doing it this way, we can lower the energy requirements because all the reactions that are happening result in a lower energy pathway to get to hydrogen. We can get into exactly how it works a little bit later. But the big thing is that we don't need to use fresh, clean water. So in terms of how green we are, compared to things like green electrolysis, I would say we're greener than they are. We use much less energy for some of our systems, and we can make hydrogen from any kind of water. You don't have to use potable water. We can use basically anything. So I don't know what you would call us in terms of the color wheel for hydrogen. I guess you would say we're greener than green. We're similar to the white natural hydrogen in essence. So there's a pretty big environmental benefit to how we do things. So it is quite a bit more efficient. So that's what we're trying to do, and that's what we ended up stumbling upon, honestly.
Just very rough numbers, Robin. how much less energy are you using on to produce that kilogram of hydrogen compared to, say, electrolysis?
Yeah, we had an external uh, energy company do analysis for us. So these are all numbers that we didn't come up with. It was third party. It's looking like we use between, depending on the temperature, because we have to heat up the water a little bit. And if you're starting in Canada, things are cold, right? So it's between 2 to 8 kilowatt hours per kilogram of hydrogen. And that's all because of how we manage our oxygen. Uh, so if you look at, I think the most efficient experimental electrolysis was somewheres around 42 kilowatt hours per kilogram of hydrogen. And that's in the academic space. That's not, production level. When you're looking at production levels, normally right around 50 kilowatt hours. So we're, 20% of what they're using in terms of energy cost. And again, that comes down to the big problem with producing hydrogen, what to do with the oxygen from the water. Uh, that's the part that requires so much energy. If you bypass that step and you're not producing O2 gas, then you can bring your numbers down, way, way, way down. And that's what we did.
Thanks very much. Pat, Robin just told us how his process can reduce the cost of producing hydrogen. But production is just part of the high cost of hydrogen, isn't it? Can you tell us why hydrogen costs so much at the pump right now? And what are the costs other than production of getting hydrogen to the consumer?
Yeah, well, thank you for having me as well, David. You can essentially think of the costs in three big buckets. So production, which Robin was talking about, delivery of the hydrogen to the pump, and then the refueling or station costs. So all the technology at the station that's needed to store and then pump the hydrogen into vehicles. And there's actually an Argonne National Lab report, which is a few years old now, but from 2019, and they did a study on hydrogen prices in Canada and determined that about 35% of the final cost was coming from delivery, and actually 50% was coming from those station costs. So for hydrogen to be cost competitive, we really need the cost to come down across all three. It's not enough for any one of them to be brought down. And some of the costs will come down over time, just as volume increases and we build more stations, things will get cheaper, we'll get better processes. So some costs naturally will come down, but then also very important to introduce new technologies. So like Robin is talking about bringing down the cost of production. And then what my company, Vern, is focused on is that 35%. So the delivery of hydrogen from the point of production to the fueling station. And so our technology is called cryocompressed hydrogen, which is a new way to store hydrogen and then distribute it, which we can talk more about later. But essentially, yeah, you can think about the final cost of hydrogen being made up of production, delivery, and then the station costs.
Thanks very much. Jay, before we get to whatever advancements Toyota is working on to make FCEVs more efficient, I think we should spend a little time discussing how a fuel cell works. They're basically a different type of battery, right? They have cathodes, they have anodes, and electrolytes like traditional batteries. And now we've basically exhausted all my knowledge of how a fuel cell operates. Maybe you can give us a bit of a primer on how they work?
Yes, from a high level, fuel cells and batteries appear similar since they both produce electricity through a chemical reaction. But the main difference, and you hit on one of the key words, was the electrolytes in the battery itself. The battery stores its energy internally with the electrolytes that flows back and forth. Whereas with a fuel cell, it produces energy as long as it has access to oxygen and hydrogen, which is stored externally. So the fuel cell can actually run for as long as it has access to hydrogen and oxygen, whereas the battery is limited to whatever it has actually inside of itself. So in the case of our Mirai, we can talk about that in our next generation fuel cells later. We store just as Pat was mentioning, the hydrogen in tanks, so we can supply hydrogen consistently to that fuel cell to drive the energy and electricity out of the fuel cell itself. But the hydrogen, as you mentioned, anodes and cathodes, hydrogen's on the anode side of the fuel cell, and oxygen comes through the cathode side of the fuel cell, and they will react with the reactor plates inside the fuel cell, splitting the electrons off the hydrogen, and then that produces electricity and goes out to whatever motors or whatever you want to power. And then those protons of hydrogen then cross over the fuel cell membranes and bond with the oxygen to form water as its sole exhaust, as it were, from that standpoint. So similar to a battery, as they're both producing electricity, but it's a very different chemical reaction in how they're actually producing electricity for the power plants.
So a fuel cell, the only reason it has a tailpipe is to get rid of the water that's being produced. There's
Correct.
nothing coming out.
Correct. Water vapor and condensed water, essentially. So in some cases, you take that and it will store, because you don't want to necessarily have it dripping all the time, but then you can release it later. Or in our case, we actually use some of that, and Toyota use some of the vapor to go back and humidify the actual cells themselves. It's really key for a fuel cell to stay humid for its peak performances.
Thanks very much. Lorenzo, thanks so much for joining us all the way from Italy, where I think it's probably the end of your working day. So Robin and Pat are telling us how we can make hydrogen cheaper, and Jay is telling us how we can make fuel cells more efficient. But you want to talk to us about an all-new type of car, the fuel cell hybrid electric vehicle. Now, we've all heard of hybrids, including the plug-in variety, but what is a fuel cell hybrid, and why is it better than gas and electric hybrids currently on our roads?
Yeah. Thank you, David, for inviting me to join this interesting panel. So let me share a non-commercial perspective from Italy on what a fuel cell hybrid vehicle represents and why it may outshine the traditional gas-electric hybrid we are familiar with. So let me start with an overall consideration before. Sustainable mobility is a complex challenge, and embracing that complexity is essential to finding a real solution. So too often singular claims serve to support a specific viewpoint, but every technology carries its own advantages and drawbacks. So there's no one silver bullet, but a true solution lies in the integration of multiple technologies. And in this perspective, fuel cell hybrid electric vehicles are quite important. So imagine a vehicle that marries the best qualities of two energy worlds. From one side, you have the hydrogen fuel cell, which, without going through any conventional thermodynamic cycle and its associated limit with the Carnot efficiency, convert hydrogen directly into electricity, with water as its only byproducts, as Jay told us. So this is very green from future perspective. On the other side, you have a battery that stored energy for instant access. Together, they form a dynamic duo that is just like a symphony of power, where every instrument plays its role at the precisely right moment. So in a fuel cell hybrid vehicle, you have that the fuel cell is not the only responsible for propelling the vehicle, but it works in harmony with the battery system. So the best approach is try to have the fuel cell provided as steady as possible stream of power while operating it in high efficiency range, with the battery stepping in to deliver an instant surge when extra power is needed, like for example during rapid acceleration or when climbing a hill. So this cooperative operation not only maximizes the overall efficiency, but also reduce the strain of each component, potentially extending their lifetime. Whenever we are talking about environmental impact with respect to the traditional hybrids, they must rely on fossil fuel. So they are emitting pollutant, even if at a lower level with respect to traditional vehicles. In constant, fuel cell hybrid operate with hydrogen, and if produced via green methods, as Robin said, the carbon footprint can significantly get down. So this is quite important. We could talk about hydrogen hybrid, perhaps, but definitely for the long-lasting period, I would say that fuel cell hybrid would be the best solution. As you can see in the picture now projected, we can have significant advantages because instead of having a mechanical connection between the internal combustion engine and the electrical motor like in the traditional gas hybrid, in fuel cell hybrid, you have that both components are electrochemical component. So also the integration together is more efficient and more flexible. So there are still challenges to overcome, of course, but a lot of research are going on, and I'm pretty confident that this advantage can play a transformative role in global automotive landscape.
Thanks so much, Lorenzo. I've got to say, Lorenzo, I've got to have more Italian engineers on my program because you explain it with such passion. I've got to say, I mean, I've never heard of hydrogen being explained with quite so much romance and everything else. Thanks very much for that. Okay, Robin, so you've made the case that your company can produce hydrogen more efficiently. How do you do it, and how does it compare as to the electrolysis we've all experimented with in chemistry class in high school?
I think the big thing that's way different is, I alluded to it a little bit earlier, is the type of water we need and what we do with the oxygen. So when you look at electrolysis, fuel cells are kind of the opposite of electrolysis. A lot of the electrolysis you can actually use as a fuel cell and vice versa. But what it does is it splits water into hydrogen gas and oxygen gas. And a common misconception that people don't really get right off the bat is that if you're only considering the hydrogen, don't think about the oxygen. This is the really important part. If you're only considering the hydrogen, that thermochemical process is actually exothermic. When I say exothermic, that means that it generates heat. And how simple our reactor is one of the main selling points. You've seen it. You've seen how simple it is and run it right into an engine. I think we have a video that you could probably bring up. And it's about as simple as it can get. Here you can see on the left-hand side, that's just our reactor pot. We keep it completely transparent because when we do demos, we want to keep it as simple and everybody can see everything that's going on. So all it does is just flow it out of the reactor into a bubbler where you just have the bubbler going just so you can see that bubbles are going through. We have some drying agents so that no humidity is getting into the engine. And it just started up an engine just like that, no problem. So the way we do it is we don't evolve O2 gas. We use the water and the oxygen on the water to make a new compound. So we move the oxygen to make new compounds. Now, these compounds are not waste. That's the big thing too. We specifically pick targets that are going to give us something of value. In some cases, the new catalyst. In some cases, it's new nanomaterials that we can use for other applications. But that's the big thing. Oxygen management is the problem with hydrogen production from water. It's not getting the hydrogen, it's getting rid of the oxygen or what you do with the oxygen. And what we did is figure out a way to move it where we want. And now since we're not evolving O2, we're off to the races. Everything takes less energy. We can make compounds that you want anyway at the same time as making hydrogen. It's the best of both worlds, really. Make something that you want, and you're getting hydrogen at the same time.
And you've talked a little bit about, and this amazed me, you've talked a little bit about the water you can use. Like, I think we should explain to most people, electrolysis requires, at the very least, fresh water, or generally maybe even distilled water, pure water. Yep. Your system can use pretty much anything. I've heard you claim that you can use tailing water, you can use wastewater. I mean, is there any limit to this?
Yeah, we've used a lot of different types of water. And as you mentioned, electrolysis at a minimum uses reverse osmosis water. I know the system that we have rejects 99% of the water just to get that pure water. So, the electrolysis world, would they say they need 11 liters of pure water? Yeah, it's probably, 10 to 100 times that, how much water they actually go through to get to that water. For us, so far we've been able to use almost any type of water. We've used pure water because we use that to do all our tests, just to kind of get a baseline. Tailings water, no purification. We get it right from the oil sands. We have barrels of it, literally. We've tried salt water. Now, salt water, there is a little bit of an inhibition. There's things that you can add to speed it back up, but then you're adding an extra component. There's an extra reaction. We're trying to keep things to a minimum. On the perhaps more gross side of things, we've used urine.
This is my favorite.
Right? Right. So it didn't matter. We used urine, and we're making hydrogen from urine. It's just these metals want to react with water and produce hydrogen. And they also like to move the oxygen around. So we just do both. Right.
I love it. I love it. I just love the concept that you could pee in your gas tank and drive off. That might be gross, but I love it. Okay, Pat, you explained why we want cryocompression, but now we all need to understand what cryocompression is. How does it work compared and and why is it much cheaper than gaseous liquid hydrogen?
Yeah, so I think it's helpful first to understand the two ways to store hydrogen today, which is compressed gas or liquid. And so compressed gas involves compressing hydrogen into 350 or 700 bar. And then liquid hydrogen involves cooling hydrogen to the point of liquefaction, so about negative 253 degrees Celsius. And there's a trade-off in both of them. For liquid hydrogen, it's really expensive to reach those low temperatures. It takes a lot of energy and hence a lot of cost. And for compressed, it's cheaper to reach that state, but it's not as dense. So there's a trade-off then when you're distributing hydrogen, you can't fit as much per truckload. And so cryocompression is kind of a combination of the two that takes advantage of the high density of cryogenic temperatures and the lower costs compared to liquid hydrogen. So what we do is compress it to about 350 bar and then cool the hydrogen, but not to the point of liquefaction. So it remains in the gaseous state. You can think of it as a cold and compressed gas. And the result of that is it's actually the highest density hydrogen. So even higher density than liquid hydrogen, which is sometimes surprising since it's in the gaseous state, and uses about half of the energy compared to liquefaction. So liquefaction, like I said, requires a lot of energy to get it down to those low temperatures. And since we're not going to as low of a temperature, consumes a lot less energy. And so interesting data point is liquefaction usually adds about $3.50 per kilogram. And all of that ends up in the final cost of the hydrogen. That doesn't go anywhere else other than to the cost of hydrogen at the pump. And so for cryocompression, we're able to save about $2 on that cost of densification is what we call it. Which then makes for cheaper hydrogen at the pump and because of the cheaper hydrogen delivery.
The number I remember, Jay, is that cryo-compressed hydrogen is about 87% more energy dense by volume than gaseous hydrogen, which would mean, Jay, you'd get 87% more range out of a Mirai if you used Vern's process, which would take your range up to about 1,000 kilometers. Wow. So that's really cool. Thanks very much. Jay, Toyota just announced its third generation of fuel cells, and it's reputed to be even more efficient. How much more? And what does that mean in terms of range and power for a fuel cell powered vehicle?
Yeah, thanks, David. Yes, we just a couple of weeks ago in at the Tokyo hydrogen seminar, we announced our Gen 3, what we call our Gen 3 fuel cell modules. We're up to about 20% more efficiency out of the fuel cell module system itself, along with, as well as better durability and and so forth. Really what this improved efficiency will mean really depends on what the customer and what we want to do with that vehicle. So 20% more efficiency, yes, we could on the same vehicle, we could run it an extra, 20% farther down the road. In case of Mirai, we get about a 400-mile range with that vehicle. We could do 480, almost 500 miles with that vehicle. Or with, from a, this is where it's fun from the engineering perspective for what we can deliver for our customers is if the customer's satisfied with that range, we can make our storage systems a little bit smaller and give that mass and that space in the car back to the customer for their usage. For passenger car vehicles, that might be very important for features. But from a standpoint of our commercial side aspects, as we're making powertrains now for heavy duty trucking, that allows that truck to go farther down the road, and also pay less at the pump potentially for the fuel that they're buying. As we all know, there is a challenge now with hydrogen, as we're talking with Robin about how to bring the price down of hydrogen. That also making more efficient fuel cells allows our customers to pay less at the pump. So that, on that synergy of what we're producing hydrogen for and then what we're asking our customers to actually consume hydrogen with. So really the efficiency improvements for our third generation will have a multitude of improvements or benefits for our customer, whether they want farther range or more attributes in their vehicles.
So here's the question I've been dying to ask. How exactly do you make fuel cells more efficient? Is it a matter of making each cell smaller or thinner and crowding more of them into one space? Or is it a matter of getting a higher voltage out of each cell? I really have wondered about this for a long time.
Yeah, those are great questions. Really, as we mentioned previously, fuel cells are electrical and chemical devices that combine hydrogen and oxygen together to produce water and electricity. And then although the chemical equation is really simple, that system is really complex. So you mentioned about making the mechanism smaller and so forth. We can make membranes thinner so that we have more reactive surface for the reactants, the hydrogen and the oxygen to react together. And then also just the overall system of pumping hydrogen in and bringing airflow in, those mechanical systems that help feed the reactants have to are also becoming more efficient and take less energy. So the overall system becomes improved, the pumps, to move the reactants and coolants and so forth. I can't really go into the specifics, but there's a multitude of different ways. Our coatings that we've made for the actual fuel cell membranes have been improved. The spatial dimensions for moving the hydrogen to allow better reaction with those membranes and combining with oxygen have all come into play, as well as the surrounding systems.
Thanks very much. Lorenzo. Okay, so a plug-in fuel cell hybrid is an electric vehicle that has a choice between two batteries. What are the advantages of having two different sources of power compared with, say, a purely battery-powered EV? How are they better than what we have today?
Yeah, sure, thanks. So actually, as you said, there are two different energy reservoirs, say. Okay, so one from a conventional battery and another one from an hydrogen tank that, as Pat has clearly explained, can be based on different technologies. And all of these technologies has a higher density than current lithium-ion battery. This means that we can extend significantly the vehicle range. And moreover, the possibility to use the flexibility with differences with the traditional battery EV can also further improve if we look at the auxiliary system. Let's think, for example, the cabin air conditioning. So in extreme weather condition, this can take up to 30% of the overall energy demand of a battery electric vehicle. Why? Because a pure battery system doesn't produce much waste heat. A sort of way where being too efficient is a problem somehow. With a fuel cell, instead, you can generate a lot of heat at high temperature, and this can be used for the cabin air conditioning, significantly impacting, okay, the capability of the fuel cell hybrid vehicle to keep a high range also under cold climate, for example. Of course, this can arise some further difficulties, like operating a fuel cell at -20 Celsius degree could be complex. So on the other side, you could have some battery auxiliary power to warm up the fuel cell and to allow the fuel cell to get operated in its high efficiency range further down to complete this kind of synergy. So essentially, what I would say is that it's thanks to the flexibility offered by having the two different sources on board that we can increase and strengthen, okay, the synergies and the benefits of both. And this really can be very important whenever we are looking at the high heavy vehicle, for example. So we know that in America, you're not used to smart for two kind of vehicle, so very light vehicle, but we are mainly talking about pickups and SUV, and in that segment, definitely fuel cell hybrid vehicle can prove its worth and can be really a significant improvement.
Okay, so and let me ask if the battery portion is plug-in and it's a large enough battery, would that mean you could use predominantly the battery source for your city driving and then optimize the also the hydrogen fuel cell for the range on the highway? Is that a simple way for some people to look at it as well?
Yeah, absolutely, absolutely. So electric vehicle and the possibility to run a fuel cell hybrid also in full electric mode is definitely the best solution for urban area, wherever you have a lot of stop and go condition, rapid acceleration, or any situation that could demand immediate high power. So it's definitely the way you should try to use, while, for example, in steady driving, such as highway cruising, where you can produce energy continuously, the fuel cell can provide its maximum benefits. So it's not only a matter of what were you using when, it's also a matter of the right application, okay, to use the right application, for the right application, the right technologies. And this is also a matter of infrastructure. So thinking about hydrogen refueling station in urban area can be quite challenges, like deploying megawatt scale fast charging station along highways pose its own difficulties. So definitely we can think about the possibility to have both full electric mode in urban area and then to get the benefit of a quite simple refueling hydrogen station along the highway in a single powertrain vehicle. So that's one of the main advantages of this kind of technology.
Sounds like a promising technology for the future, for sure, Lorenzo. Thanks so much. Okay, so Robin, let's get down to the nitty-gritty. The revolutionary part of your thermocatalytic process seems to be the catalyst itself. So what's so special about it? Is it the material, or is it how you process? What makes this system that Dark Matter Materials has come up with so different from what we've done in the past?
The big difference is how low the temperatures have to be to activate or to have an active compound to do all these transformations. If you look at other thermochemical processes, however you want to trust Wikipedia, it's on there. The lowest is around 500 degrees Celsius. Most of the time, they're well above 1,000 degrees Celsius. Ours, in some of our systems, they'll start producing hydrogen at room temperature. The other ones, they start producing at about 45 degrees. And then, as I mentioned before, it's exothermic. And actually, the one that you saw is actually one of the ones that self-heats. And it'll heat up by itself from 40 degrees to 80 degrees. And then it just takes off. And Jay mentioned something that's really important, actually. if you can make things smaller, then you can make things more active. So I like this analogy. Just think that, okay, you spilled a whole bunch of salt on your table. Well, now you have this big pile of salt. Only the stuff on the surface of this pile is active. That's the only part that's actually producing hydrogen. It's the stuff that's on the surface. Now, if you take that pile of salt and spread it all over your table, now you have a whole bunch more active sites because you made a whole bunch of small piles instead of one big pile. So our catalyst is different from what's other similar compounds. It's much, much smaller. We're talking 5 nanometers, really, really, really tiny, and it's a different shape. So when you're looking at heterogeneous catalysts like solid catalyst, you have to consider the size and you have to consider the shape. And we made it a different size and a different shape than anybody else has ever made before. And that's what makes it work, essentially, is we increase the number of active sites by making things as small as possible. And when you do that, you really start to stress out the bonds. So just imagine that you want a chemical bond to have a certain angle between the different elements for them to be stable. And if you start changing those angles, well, now those bonds are less strong. So when we make it smaller, you make all these bonds weaker, and that lets us move the oxygen where we want. So you wanted the bond to be strong enough to bind with water, but not so strong that you have to heat it up to 1,000 degrees to get rid of the oxygen. So we're kind of right on the fence. You know, we fall off one side and the reaction's going to work. We fall off on another side, we have to heat it up too high. So we're kind of like riding this fine line between reactivity and stability. You want things to be stable enough, but also reactive enough. And that's a really, really tricky thing to do in catalyst chemistry. You can't have both at the same time. It can't be stable and reactive at the same time. You have to find that balance. And by making things this small, we found that balance. And truthfully, we didn't make this catalyst to react with water on purpose. We're making it to react with essentially alcohols to do a similar process. Never in our wildest dreams did we think it was going to react with water like this, but it does. So we did a little happy dance, right? We're like, well, this shouldn't be happening, but it does. And you've seen it. People only believe it when they see it. And we've given so many demos now to skeptics that they come in, they see it, they go, I'll be darned, it works. Yep, sure does.
So it sounds like so many discoveries. It was a happy accident. So fantastic. Pat, this cryo, why do I have such a hard time with cryocompression? This cryocompression stuff sounds promising. Have you tested it on any vehicles yet? What were the results?
Yeah, so we actually did towards the end of 2024. We tested it on a Class 8 truck. And so for this test, we used it as the onboard fuel storage. So the hydrogen that powered the truck, essentially. So it was a saddle-mounted cryocompressed hydrogen tank that we used to then fuel the truck and do some test driving. And the results were successful. We achieved the density and the range extension that we were hoping to. But really where we see the most immediate application is not as the onboard fuel storage. It's actually for hydrogen distribution. And so essentially you can think of 2 different ways to use very similar storage technology. One is store like the fuel tank, storing the hydrogen to power the truck. Another is essentially the same tanks on the back of the truck and now being used to deliver hydrogen via truckload. So back to that hydrogen delivery part of the value chain that we talked about. And so that's where we see kind of the most immediate and most attractive applications of our technology is for hydrogen distribution to the fuel station or to a warehouse for forklifts or for whatever end use of hydrogen it might be. But this test was still great validation that it works. It was kind of a rigorous off-road track, so it was good to validate that it withstood those conditions. And now we're moving more towards pilots for hydrogen distribution. So delivering hydrogen to be used by end users for different applications.
Thanks very much. Jay, one of the problems for battery-powered cars is their range in the winter. And of course, Canada is famous for, well, its winters. So are fuel cells better suited for cold weather performance than traditional batteries? And how do you go making a fuel cell Canada friendly?
Yeah, good question, David. You know, the interesting thing is with the as we were developing Mirai, we actually used Yellowknife. We were up there testing, spent many winters up in Yellowknife in the extreme weather. You know, we recognize that our customers will live and travel to many areas, wherever they want to go, whether we're talking 50 degrees C in Death Valley, or minus 40 up in Yellowknife. We really test and go to those sub-freezing climates to push and develop our advanced control systems. One of the as you mentioned, as you get a battery cold, its charge ability to release charge reduces. With the fuel cell, because we're feeding hydrogen and oxygen into we can still produce as much as we can as reactants as we provide. And also, as mentioned earlier, and I'm sorry which of our panelists mentioned it, it is exothermic reaction. So it is heating itself in the fuel cell as we're generating energy to keep the fuel cell warm. We actually can use that to supplement cabin heat for the vehicle itself as well as we produce and generate energy for not only driving but for running the systems in the auxiliary systems in the vehicle itself. So we spend a lot of time in a lot of different environments, and especially up in the frozen areas of Canada to develop our fuel cells.
So I'm going to put you on the spot here, just a thought.
Sure.
Would that mean that a fuel cell vehicle loses a little bit less of its rated range in extremely cold weather compared to a battery, do you think?
I would say its rated range will be less affected by temperature than significant, similar to a gasoline vehicle, because we're reacting to fuels that are stored externally, so we can still provide the same energy into the systems.
Thanks very much. Lorenzo, so are you putting this theory about hybridizing battery and fuel cell powertrains into practical application? Have you built anything using this combination platform? And what do you hope to prove with your experiments?
Yeah, absolutely. We are indeed moving beyond the theoretical models. At the Sustainable and Clean Energy Research Group here in Tor Vergata University, we are developing a prototype that integrates both power sources into a single platform. As you can see in the video, with a particular focus on light personal mobility. This is to try to emphasize the economic viability by leveraging standard component, because you cannot have so sophisticated component on a light personal vehicle, in conjunction with advanced control strategy. So our research is centered in developing tailored control strategy that learn from driving habits, from road conditions and traffic patterns through machine learning techniques applied to historical data. So the control strategy learn itself how the vehicle has been used in order to make the smarter as possible the control system. That is, try to maximize the synergy we were talking about between battery and hydrogen source on board. We are also trying to investigate different kind of low pressure hydrogen storage method, such as metal hydrates, that are some systems that can store hydrogen by absorbing that inside the metal structure. There are some complexities due to the heat management in that kind of storage, but definitely this could help, together with the other technologies, in simplify the infrastructure requirement by lowering the pressure on board and therefore lowering the pressure needed for refueling. So we are expecting to complete the hybridization of the vehicle shown so far in the video within the next few months, and we try to get some exciting results to share later in this year.
Thanks very much. Robin, so far we've only talked about hydrogen and vehicles, but as you've mentioned, your process can also do other things, break down other materials, including plastics. Can you just give us the high-level version of all the things it can do?
Yeah, a ton of different things, actually. You've seen some of them. You saw the demo of the battery. We use the exact same materials and we made a single cell battery out of it that was, what, 2.8 volts when you saw it, somewhere around there.
Yeah.
And we had it completely open to air. We didn't do any kind of protective thing to emit water or anything like that. You saw me dunk it in water and remeasure the voltage, and it was still 2.8. So, I mean, being able to make batteries 2.8, 2.9 volts, water safe, air safe, I really love that technology. That's another one of those things that was unexpected. And it can also break down plastics. Now, we've since made even better catalysts, kind of derivatives of what this catalyst is. And it can break down polyester, PET, polyethylene terephthalate, like your water bottles, your polyester shirts. And it breaks it right down to monomers at probably about 100 degrees cooler than I just saw a paper this morning that was 100 degrees hotter than what it is, than what ours does. So it does it at around 200 degrees. We get 95% mass balance back. So we get the monomers back, actually, and we repolymerize those monomers into fresh plastic. So we decomposed the plastic, repolymerized it back on purpose. Ridiculous yields, 95 plus. The catalyst we reused. It's just honestly, like the plastic stuff is as exciting as the hydrogen stuff. So I would like to say, I mean, Dark Matter Materials is more of a clean tech company. We're not just working on hydrogen. We're working on, we see where the problem areas are and we're trying to clean stuff up. So this catalyst can seem to do a lot of those things, or just modifying this catalyst a little bit will get us there.
I've got to say, if I hadn't seen it for myself, I probably would have thought it was all magic. And that's my polite way of saying something far ruder. Pat, so you mentioned cryocompression. Oh my God, I got it right. Refueling works for trucks. Could it work with passenger cars? And to get a little more specific, could your cryocompression station and fuel be able to fill up a Toyota Mirai, which uses a more traditional high pressure gas tank?
So yeah, the short answer is yes. There's no reason cryocompressed hydrogen can't work with light duty vehicles. So first, thinking about kind of the onboard fuel storage, it can work, and it has been done using cryocompressed hydrogen to power light duty vehicles. The question is always just comes back to kind of that trade-off of cost and density that we were talking about earlier. And so, as I mentioned, like compressed hydrogen is not as dense as cryocompressed hydrogen, but it's cheaper to reach this state. And so it really depends how much energy a specific vehicle needs to store on board. And comparing light duty vehicles to heavy duty vehicles, you can think about a big truck that weighs 80,000 pounds and needs to drive 400, 500 miles a day versus a passenger vehicle that weighs a fraction of that and probably drives 30, 50 miles a day, needs a lot less energy. So often it doesn't make sense as the onboard fuel storage for light duty vehicles. It just doesn't justify the increased cost of densification. But one place where it can still make sense is in delivering hydrogen to those fuel stations. And so depending on how far you're delivering it, where the hydrogen's coming from, cryocompressed hydrogen is most often the most efficient way to deliver hydrogen to fuel stations. And so like we were talking about, that just brings down the overall cost of getting hydrogen to the vehicles. So in the light duty segment where we see cryocompressed hydrogen having an impact most immediately and most strongly is in that midstream of the supply chain and delivering hydrogen to fuel stations, making it cheaper and easier to get hydrogen where it needs to go.
Thanks very much. Finally, Jay, for a lot of Canadians, the major question when you're looking at a new automotive powertrain is how long will it last? So it has an enviable reputation for reliability. What's necessary for your team to ensure that fuel cells will be just as reliable as, say, a four-cylinder Camry?
Well, honestly, David, it's really very simple. From our development methods, the standards that we use for our powertrains are essentially the same across the vehicle lines. So what's good for a Toyota Mirai is the same as what we apply for the vehicle that's a Toyota Camry, that's a gas-powered vehicle. So overall, the vehicle side requirements are not any different. So we'll send the Toyota Mirai, for instance, through the same durability and vehicle usage conditions that a Toyota Camry with a four-cylinder would have to go through. So looking at breaking down from the vehicle side, break their subsystems down into their subsystems, and then down into the individual components, and then we make sure that those individual components will be able to provide the same level of durability and reliability and quality all the way up to the full vehicle assembly. So even though it's a different technology, we still hold them to the same standards of output for our customer, our QDR, as we call it.
So my dad got about 500,000 kilometers out of a four-banger Camry. So let's hope that Mirais go just as far.
Should expect it.
Lorenzo, so far, we've covered the basics of a fuel cell hybrids operation, that it uses a battery in the city and hydrogen on the highway. But I know from the development of traditional hybrids that it's not nearly so simple as that. Your specialty is the protocol of which energy source does what when, without losing us PhDs. How are you optimizing range and efficiency in your experimental FCHEV?
Yeah. Thanks, David. So the actual innovation and the point where you can get the maximum of efficiency is in the way you make the two power sources integrated each other. So rather than some simple rule-based strategy that are designed to operate the battery source or the hydrogen source when in some specific application, what we are trying to develop and where the actual research is going on is to try to make the system as smart as possible by learning by itself. So with some new data-driven methodology, with some machine learning approach, you can make the system learning by what it's doing. Okay, by operating the vehicle, you can actually understand what is the best way to use it in that specific application. That really depends on the way you are using the vehicle itself. So on your driver habits, there's some driver that is more aggressive than other. So specifically taking the history of the way the vehicle is used, we can develop a tailor-made control strategy to maximize its efficiency. There are some general considerations. Like we said, the fuel cell doesn't like too many high variation in power, too rapid variation in power. So we would like to keep as stable as possible in its maximum efficiency. But you can do that perhaps forecasting what is going to happen. So what we are trying to develop is some strategy that can classify. Let's make an example. You are commuting from home to work. I'm not expecting that you are going to have very different driving scenario one day by the other. So by learning what is the current situation that you are having by driving your car, we can try to make the control strategy operating in advance. And this can really help by keeping the fuel cell and the battery working in their best and most efficient way. So that's really the things that we can couple together with some new technology like Internet of Things, some edge computing that can share information with the infrastructure in the next future. So this can really allow the system to have some forecasting features that can definitely help improving the overall efficiency of this vehicle thanks to their flexibility.
Okay, guys, that's the last of the questions I had to ask. So let's turn to a few viewer questions, of which there were many and surprisingly detailed as well. We have just a few minutes, guys, please. So 30 seconds per answer. First up, Lowell asks, are solid state battery and hydrogen fuel cell technologies competing or complementary? I think this is a question for both Lorenzo and Jay. You first, Jay.
Yeah, that's a good question. We'll say complementary. We always, of course, solid state batteries have a role as a single vehicle, like BEV vehicles, but also within the powering, as Lorenzo was mentioning, we have to pair a fuel cell module with a battery type, and we are kind of battery agnostic between solid state, nickel, or lithium within our fuel cell type vehicles.
Lorenzo.
Yeah, I do agree.
Competing or complementary?
Definitely complementary. Whatever is increasing the energy density can make the vehicle lighter, more capacity on board. So all the benefits that can help increasing range and having more efficient. So still having the flexibility we were talking about, but still rely on hydrogen can be produced in wherever you have an excess of renewable, and that would be definitely the best way to go. So complementary, absolutely.
Thanks very much. Henry has a question that is almost certainly directed at you, Robin. He asks about pink hydrogen, which is nuclear-powered electrolysis, and turquoise hydrogen, which is pyrolysis. Are either feasible, and maybe even how do you compare your process to any of these?
Yeah, I could see nuclear power pink hydrogen as being feasible. I mean, you have a lot of waste heat, right, with nuclear power. So even if they're just using the waste heat and the steam coming off to do electrolysis, yeah, I could see that. In terms of methane pyrolysis, the scale that you would need to do, oh gosh, I hope I'm not too choppy. I just got a warning. For methane pyrolysis, there's actually more value in the carbon that they get than there is from the hydrogen. So I don't see methane pyrolysis being done at the same scale as steam methane reforming. It does have promise, but the value is actually in the carbon, not the hydrogen, for that process.
Thanks very much. One last one from Todd from Zero Avia, a company that wants to produce hydrogen-fueled planes. He asks, can CCH2, that's geek speak for cryo-compressed hydrogen, be made to work in aircraft? Pat, that's definitely for yours.
Yeah. So again, the short answer is it can. In all of these applications, it comes down to the different considerations. So just like between light duty vehicles and heavy duty vehicles, there's different considerations for aviation. And in aviation, you need a lot of energy, and weight is obviously very important. At that scale, we actually think liquid hydrogen will have a slight weight advantage relative to CCH2, but CCH2 will be a bit cheaper. So both have their kind of advantages and disadvantages, but I think kind of an open question which one will actually be the best technology for hydrogen-powered aviation.
Thanks very much. So that's all we have time for today, folks. First off, I'd really like to again thank Jay, Pat, Robin, and Lorenzo for joining us. I'd also like to thank Toyota for the support that makes this discussion possible. Most of all, thanks to all of you who listened in today. It's because of you that we can put together these shows. And if you want to know any more on the subjects discussed here today, just Google Motormouth on Driving.ca. Thanks very much for listening.